Now the last part of this chapter is your resonance. Now this is very important. You will find it out very important in organic chemistry. You will see it. Clear? Now what is resonance? See, now the definition is quite bigger. Now in case of certain molecules, you will find it out. A single Lewis structure cannot explain all the properties of the given molecule. Listen carefully, children. Listen carefully. In case of certain molecules like ozone, carbon dioxide, benzene, carbonate, sulfate, nitrate, in this way many molecules are there. So in case of certain molecules, a single Lewis structure cannot explain all the properties of the given molecule. All the properties of the given molecule means a particular structure explains one of the properties, another structure will explain another properties, another structure will explain another properties. You will say so many structures. Yes, that structures, the so many structures you will be getting now, that is called as contributing structures or canonical structure. Canonical or contributing means similar structure. Alright, canonical or contributing means it is called as similar structure. Similar, we can say that. Now the molecule is then supposed to have many structures. Alright, as I said you that in case of certain molecule, a single Lewis structure cannot explain all the properties of the given molecule. The molecule is then supposed to have many structures, which I was just saying you, canonical, similar, contributing. Alright, clear? The name which I was saying you. Each of which can explain, alright, most of the properties of the molecule, but none can explain all the properties of the given molecule. Each of which can explain some of the properties of the molecule, but none can explain all the properties of the molecule. Alright, the actual structure, now listen carefully, the actual structure lies in between these contributing structures. The actual structure, alright, lies in between this contributing structure or canonical structure and is called resonance hybrid, and is called, this actual structure is known as resonance hybrid, which lies in between this contributing structures or canonical structure and the different individual structure. Alright, is called as what? Already I have said you, that is called as resonating structure or canonical structure or contributing structure, whatever you can say that, and the phenomena is known as resonance. So what I said, once again let me repeat, that in case of certain molecule, a single Lewis structure does not explain all the properties of the molecule, a single Lewis structure. The molecule is then supposed to have many structures, alright, each of which can explain most of the properties of the molecule, but none can explain all the properties of the given molecule. Alright, so as a result, that is, the actual structure is in between this contributing structure, which is called as resonance hybrid, and the different individual structure is called as what you can say resonating structure or canonical structure or contributing structure, we can say that. And this phenomena, this process, phenomena means process, is known as resonance. Got it? Understood that? So resonance, let me tell you, the contributing structure which I am going to show you, the canonical structure which I am going to tell you, are all theoretical. Remember it. It is all theoretical. Practically, the resonating hybrid actually exists. Practically, the resonating hybrid exists. So as to explain the resonating hybrid, listen to each and every word, children. Alright, so as to explain the resonating hybrid, I require some structure. Alright, that is called as canonical structure, which does not exist, which is existing only pen and paper, theoretical. Alright, which actually does not exist, is completely theoretical. I am saying you right from the beginning. The canonical structure which I am going to draw it. The actual structure is the resonating hybrid. The actual structure, that is the practically which exists, by which we come to know all the properties of the given molecule, is your resonating hybrid. Canonical structure does not exist. Alright, now coming to examples, let me just tell you some rules for writing the resonating structure. You can also write it down, the rules. The contributing structure should have the same position of atom. Contributing means the canonical structure. First I will draw the canonical, then I will draw the resonance hybrid. The contributing structure should have the same position of atoms. They should differ only in the, what you can say, position of electrons. They should differ only in the position of electron. First you write it down, then I will tell you, I will explain it. Alright, this is point number 1. Point number 2, the contributing structure should have the same number of unpaired electrons. It should have the same number of unpaired electrons. Number of unpaired electrons should be same. Only the position of electron will differ. The number of atoms will also be the same. Understood? Till now. Point number 3, the contributing structure should have this nearly same energy. Same energy. Always remember that in all the cases. Whether it is molecular orbital theory, whether it is hybridization, whether it is resonance, should have always the same energy. Alright? Nearly. We can say that. So contributing structure should have nearly same energy. Alright? Point number 4, the contributing structure should have negative charges on the most electronegative atom and the positive charge on the most electropositive atom. That means suppose a structure is there HF. So hydrogen is positive. So the positive charge should be on the hydrogen atom only. And the negative charge should be on the fluorine atom only. Suppose if you are writing H negative, F positive, it does not exist. That contributing structure is a wrong one. Right from the beginning I am saying. That is, a positive charge should exist on the most electropositive atom, the negative charge should exist on the most electronegative atom. Alright, in a contributing structure, the like charges should not be what you can say present on the adjacent atoms. Why? They will repel. Alright, while unlike charges also should not be so far from one another. Why? Because the attraction is going to decrease. Alright, again I repeat. In a contributing structure, the canonical structure which you are going to draw to reach the resonance hybrid, the like charges should not be present on the adjacent atom. Adjacent atom, it should not be present side by side. Why? Because it will repel, na? If it is present, positive, it will repel. Similarly, unlike charges also should not be widely separated. Why? Suppose if one atom is here, another atom is here, positive here, negative is here. What is the force between them? Alright, the force will be not so much. That what force? Attractive force, na? Opposite means attractive force. The attractive force is not so much that when the atoms are far apart, they will pull one another. No. Alright, that means the bond length also should not be so big between the two atoms. If the bond length is much more bigger, if the bond length is higher, then the opposite charges which will exist between the two atoms will cancel out and the molecule will be unstable in nature. Alright. So hence, like charges also should not be present in the adjacent atoms and unlike charges also should not be far apart. Far apart means the bond length of between the two atoms should not be so large. Alright. So these are the rules, so to say. Alright. For that is drawing the resonance structure, canonical structure. And let me tell you another definition. Resonance energy. The difference in the energy of the resonance hybrid and the most stable contributing structure is known as resonance energy. The difference in the energy of the resonance hybrid. See, you will be doing so many contributing structure, but one will be what you can say existing in between all the structure. One particular will be existing, which is called as the resonance hybrid. Already I said you the definition. So difference in energy between the resonance hybrid and one of the canonical structure, which is most stable out of so many structures. The difference in energy, that is called as resonance energy. And always remember that resonance energy always should be least. Always it has to be least. Resonance energy. Because more the resonance energy will be released. Alright. In case of resonance, actually what is happening, when I will draw the canonical structure, you will see what is exactly happening in resonance. The energy is distributed. More amount of energy is distributed. Less amount of energy will be left in the compound or the species, and more stable will be the compound. Actually, in resonance, when we draw theoretically, we draw structures, canonical structure. But practically, you know what is happening in resonance. Listen carefully. Practically, in resonance, energy is distributed. More number of canonical structure, more stable is the resonance hybrid. Remember it. This is one of the characteristics of resonance. Alright, the contributing structures should not, the contributing structure does not have any real existence. Already I said it. Alright, as a result of resonance, the bond length in a molecule becomes equal. Alright, Due to resonance, what happens? The bond length becomes equal. Otherwise, if you see the canonical structure, you'll find double bond is having a particular bond length, single bond is having a particular bond length. In one molecule, like in ozone molecule, oxygen, oxygen, double bond is having another bond length, then oxygen, oxygen, single bond is having another bond length. Why it is so? But practically it is not so. I will tell you now why it is not so. Alright. So hence, in case of resonance, the bond length is equal. In resonance hybrid. Alright. So resonance hybrid has lower energy, hence it is greater stability. Alright. So hence, when you will be explaining in organic chemistry, a particular structure will exist. How will you say? Due to resonances exist. Due to resonance. Because due to resonance, what happens? Energy is distributed. More the energy is distributed. How more the energy will be distributed? More the number of canonical structure. So more energy will be distributed. If the canonical structure will be more, energy distribution will be more. When I am drawing the structures, practically what I am doing, listen carefully. When I am practically I am distributing the energy. More energy is distributing, less energy will be remaining in the compound and more stable will be the compound, and that is called as resonance. That is known as resonance. Basically in resonance, again and again I am saying energy is distributed. Canonical structure which I am drawing, basically I am distributing the energy in the canonical structure. Alright, so greater is the resonance energy which is liberated. Greater is the stability of the molecule. Because more energy is liberated, less energy will be remaining and more stable is the molecule. Greater is the number of canonical structure, already I said you, that is greater is the stability of the molecule, so to say. Alright, so hence let me clarify, canonical structure does not exist, it is completely theoretical, it has got no real existence and there is no equilibrium. When I will be drawing the sign, this sign, it is not an equilibrium sign, mind it. Alright, it is similar sign, it is not an equilibrium sign. Don't think they are equilibrium, that the structure lies in equilibrium with one another. Alright, that you need to understand it. Okay, now we will see some examples of resonance. Let me take the examples of ozone. Alright, so this is ozone molecule. What I find is that here the double bond is there and here the single bond is there. So here that means 4 electrons, so 1, 2, 3, 4 more electrons, 8. Here it is 1, 2, 3, 4, 5, 6, 2 electrons here, and here it will be 1, 2, 3, 4, 5, 6, 7, 8. Alright, if I draw it, I will be getting this one. Alright, so this is one canonical structure. This is one canonical structure. From here I have drawn it. From the electron dot diagram I have drawn it here. See here, this is double bond. What is the other canonical structure? I should draw on the side, understood? So let me draw it below. That is a little better. Otherwise you will also draw it in this way. So see here, this is a canonical. What is the canonical structure it can be? So the canonical structure can be this. See here. Alright, but the resonance structure is not this. Resonance is this. Now, how do we come to know? If you see, the oxygen-oxygen single bond is 148 picometer. And oxygen-oxygen double bond is 121 picometer. Because it will be little bit less. Double bond means slightly it will be less. Double bond. Alright, but practically, it is neither 121 nor 148. It lies in between. In this resonance hybrid, the bond length lies in between. How much it is? It is 128 picometer. So 128 lies in between 148 and 121. That's what I said. The resonance hybrid lies in between these two canonical structures. Alright, so here you can see that the electrons, you put the electrons here. Alright, here also you put the electrons. You need to put the electrons. Clear? You can see. So these two are the canonical structure. Now this structure and this structure, neither can explain all the properties of the ozone molecule. But this structure explains. Which properties? The same properties it is. Here it is saying 121, it is 148. How it is possible? One oxygen in a particular molecule, one oxygen atom will have 121 picometer, another oxygen atom will have 148 picometer. But practically, we see, when we see it practically, we find it out, it is neither 148 nor 121, it is 128 picometer. For that purpose, we require resonance. Because this two structure does not explain the complete or all the properties of the ozone molecule. This particular structure explains. But it explains, see, one of the bond length it explains that what is the bond length. And also it says that it is V-shaped. Alright, it is bent shaped. Alright, here the oxygen atom, the energy is equally distributed. This line what it shows, the energy is equally distributed between these two. So these two oxygen atoms are equally negative, as well as this particular one, they are equally negative. Alright, but here it shows one is double bond, it is more negative, and single bond, it is less negative in nature, we can say that. But here you can see the energy is equally distributed and it is equally negative in nature. Alright, so this is a resonance hybrid and these two are the canonical structure. Same thing, we can say that in case of carbon dioxide molecule. Alright, in case of carbon dioxide molecule. So, I hope you understood this. Now, in case of carbon dioxide molecule, you see, so what is the structure of the carbon dioxide molecule? This is the structure. O double bond C double bond O. Clear? So, if you see then, I can write the canonical structure in this way. I can draw the canonical structure in this way. That is, this bond can come here. And as a result, this will be single and this will become triple bond. So, oxygen, here it is triple bond and here it is single bond. So, due to single bond, this what you can say, what you find is, as it is what you can say triple bond here, got it? As you can see it is triple bond here, or you can do it in this way also. If you don't understand, you can do this one in this way. So, here it goes triple bond, you can say that. So, this one you make it as triple. That also can be said. This one you make it as triple. So when this becomes, that is nothing but triple bond. So what you find is here, this oxygen is having how many electrons? This is 2 electrons and 6 more will be there. And this is having how many? 1, 2, 3, 4, carbon is 8, no doubt about it. And this oxygen is 6. So here it is. So here it is excess and here it is deficiency. One is negative, another is positive oxygen, not possible. Another canonical structure which I was drawing it previously, that you can see. What it can be, now this oxygen can be triple bond and this can be single bond. Alright, so this will be positive and this will be negative. Alright, so number of electrons here it is same. Alright, the number of electrons it remains the same here. So either the structure can be this or this. Now when we see this particular structure, alright, so if I say this is the carbon dioxide molecule, if I take this molecule and explain the carbon dioxide molecule, then here carbon oxygen bond length is how much? That is in case of triple bond, the bond length is nothing but 110 picometer. This is 110 picometer. If I take this molecule and explain, it is 110 picometer. And carbon oxygen single bond is nothing but, carbon oxygen single bond will be always it will be there is more, it will be 100 and that is 15 picometer, you will be finding it out. Clear? 115 picometer. But so what you find is that in case of carbon oxygen triple bond, it is 110 picometer, and in case of what you can say this carbon oxygen single bond, you will be finding it out, it is 115 picometer. But it is neither 115 nor it is 110. It lies in between that. Alright. So it is how much it is? 121 picometer. Alright. It is. So what I said, it is 110 picometer, that is carbon oxygen bond is, triple bond is, and that is it is found to be as that each carbon to oxygen the bond length is this one is nothing but sorry, I am very sorry. This is 110, this is 121. I am very sorry, and this one is 115 picometer, which is lies in between. I am very sorry. So it is in this way. What you find is that it is 110, this is 121 picometer, so hence it is 115 picometer, which is lies in between. So this structure is the actual structure, the resonance hybrid. This structure are the canonical structure. So these two structure does not explain all the properties of the carbon dioxide molecule. It says that one oxygen is negative, another oxygen is positive, and the bond length is also differing. Same thing, this structure also explains the same thing. But in this particular structure, we find that both oxygen molecule is equally negative in nature, equally negative. Got it? And the carbon atom, as a result, what you will find is that it will be 2 plus positive. Alright, so you can see the negative charges are not so, the like charges are also, what you can say is far apart from each other. The like charges, they are far apart from each other, the like charges, they are not repelling, and the unlike charges are also, what you can say, closer to each other, we can say that, which is 115 picometer distances. Clear? So in this way, this is the resonance hybrid, which actually explains the structure of the molecule. You know the carbon dioxide molecule is this, but how it came? Some they say it should be this, some they say it should be this. But these two are the canonical structure. These two are the theoretical structure. But this is the actual structure. Got it? This is your resonance hybrid, which explains the actual properties of the carbon dioxide molecule. Here it shows one oxygen is positive, it is negative. But here it shows both the oxygen are equally negative in nature. So in this way, we can explain many other molecules by the help of resonance. We can explain the example of benzene, we can explain the example of sulfate, we can explain the example of carbonate, then nitrous acid, carbon monoxide, so many, nitrate and so many. Got it? Again I repeat, where you don't find that a particular structure does not explain all the properties of the given molecule, then we require the resonance structure, which is actually existing, but canonical structure is theoretical. These two are theoretical. Just that to say that this structure is correct, I require these two structures. That this is not possible, this is possible. I require this structure, understand this particular thing. You might be saying that I am knowing this particular thing. Yes, you know. Who's saying that you are not knowing? But how it came from this two. Initially we thought that carbon dioxide should be this or it should be this. But it's neither this nor this. It is this. How do we come to know? From the resonance hybrid we came to know. So many of the structure which you are seeing it today, they are the resonance hybrid. But initially it was thought that the structure should be something else. And that particular structure was known as a canonical structure. I hope you got it about resonance. Thank you.